Water scarcity critically impacts billions of people across the globe. The UN reports that more than 2 billion people lack drinking water, 2.3 billion people lack basic hygiene, and more than 3.6 billion people lack safe sanitation. In fact, it is believed that 129 countries are lacking sustainably managed water resources. As such, it was decided by the UN to include clean water and sanitation as one of the Sustainable Development Goals, which will provide a blueprint for peace and prosperity for people and the planet, now and into the future. The Sun2 H2O team investigates the potential to divert water treatment waste from landfill and the use of solar energy to deliver clean water to hard-to-reach communities that lack it by very simple means without increasing the complexity or affordability. In general, large-scale desalination plants are located next to the ocean, meaning fresh water will need to be transported via long-distance pipelines that are very costly to build, or get transported via trucks that can have an expensive fuel cost. These large-scale desalination plants also use significant amounts of reverse osmosis membranes, with membranes having an average lifespan of 1 year. Roughly 18,000 tons of these end up in landfill every year. Our solution is to divert these modules by converting them to lower-grade membrane filters by using regular, cheap chlorine bleach that can be purchased from supermarkets. The bleach strips away layers from the module, revealing larger pores, which can now be categorized as lower-grade nanofiltration and ultrafiltration modules. These can still be reused in a variety of water treatment applications and can be powered by solar power as long as there is a sufficient solar resource. The design of the system means that the humanitarian implications are endless, whether that be for water relief in disaster-hit locations or areas where municipal water is unavailable or highly stressed and polluted.
Our project has identified locations in the rural areas of the Northern Territory which can benefit from these recycled membranes. Specifically, there are arid regions in the Northern Territory which are very susceptible to water stress and poor quality of groundwater. In fact, it's estimated that there are at least 28 remote communities in the Northern Territory with dangerous levels of hazardous minerals. Our solar desalinator system will enable these communities to turn this stressed water into healthy drinking water that is made cost-effective and self-sustainable through PV. Our desalinator is simple and modular, able to be transported on the back of a truck and set up quickly in the areas that need it most. The solar desalinator works via pumping undrinkable bore water from the ground, passing it through a preliminary filter to remove any large organics, and then through a pressurized loop which squeezes out the H2O whilst leaving behind bacteria, salt, and other organics that we don't want. With just one 300-watt solar panel, we can produce 20 litres of fresh water per hour. This system is different from conventional desalinators due to our unique straight recycled membranes, which minimizes blockages in the system, our distinctive energy recovery method, which minimizes the energy required to run the system, and our UNSW developed light sterilization device, which ensures that no nasties can make it through to the clean drinking water.
With previous system, it can achieve a water recovery rate up to around 50%, but to increase the water recovery rate for zero liquid discharge system, we postpone to use an additional solar steel for extra brick treatment. This solar steel is work on a repeated evaporation and condensation cycles with the help of sunlight. A special angle of reflector has been built by UNSW to concentrate the sunlight from all directions to the ceramic tube to maintain the temperature difference for maximum efficiency.
Overall, our system can become a new green solution for water treatment to ensure the project implementation happens smoothly. The viability of this project has been analyzed from a risk, costing, building period, and criteria for success perspective. The biggest challenge for this project will be the component maintenance if there is no service team available locally. The lifetime of the membrane will vary due to the usage and water quality, while scheduled cleaning for glass cover is needed. A solution to this will be training the locals to be responsible and keep on track of the system and components regularly. Since our solar desalination system uses 3 reverse osmosis modules that were planned to be thrown out, and the simple solar steel design, we estimate that our system can produce fresh water less than $2 per per meter cube. This cost of water is less than the water tariff applied by the New South Wales government by 20%. Most of the system will be prefabricated off-site, while the modular design is ready within hours of delivery for operation. For mid-term success criteria, a prototype that incorporates solar stills and recycled membranes will be created and stimulated to perform analysis of water production. In the last stage, it will be required to check whether the project achieves the design expectations by implementing it in proposed locations. Our design not only benefits rural areas, but also conscious communities that aim to reuse their wastewater. It is cheap and a self-sufficient approach to clean water powered by the free solar energy.